Hello, welcome. So today what we're going to be doing is walking through a little activity that we can use to determine the number of degrees in the central angles of any convex polygon. And so what we mean by convex is that it's basically a polygon that we're used to seeing where all the corners sort of point outward. As opposed to a concave polygon, which is one where the corners alternate between in and out. So if you think of like a star, that would be an example of a concave polygon because the corners certain corners sort of jut inward as opposed to outward. So the activity that we're going to look at is specifically for your standard concave polygon. So we know from previous lessons that the sum of the interior angles of a triangle is always 180 degrees. So if I'm looking at this first angle, it's clearly a triangle. So we know this guy has a sum of 180 degrees if I add all three of these angles. We also know from previous lessons that quadrilaterals are supposed to have a total of 360 degrees, but if we assume we didn't know that and we were trying to figure out the number of degrees in the quadrilateral, we could just sort of take a line, cut it down the middle right here, and we notice we have a pair of triangles. So if I add these three angles here, it would give me a 180. If I add the three angles on the right side, it would give me 180. So altogether, I have 360 degrees. So when we get to the pentagon, the five-sided figure, we need to take a similar approach. And there's different ways that we can cut these these figures into triangles to kind of follow the same strategy we did for the quadrilateral. The quickest way to do it is to break it up so that all of the angles of the triangles are also part of the vertices of the pentagon. In other words, I want my triangles to be made of the edges of the figure as opposed to cutting them from the center. So if I cut them like this, I get what I want. There's many ways you could do it. If you cut from the center or where they crisscross in the middle, you can still figure out the answer, but it might be a little bit more complicated. There's an extra step in there that for the moment I would like to avoid, and there's any number of ways we could cut it up, and the more complicated we make it, the more we have to think about, and let's just not go there for right now. Let's keep it simple and say that I cut from right there. And again, I could do this from any vertex on the figure, but I just chose to do the top because it was easiest to see at the moment. So if I take these three angles, add them up, I get 180. If I take these three angles and add them up, I get 180. And then if I do the same over here, 180 degrees. Altogether, 540. And we can continue this pattern for any of these polygons. So hopefully we're sort of picking up on the method that we're using, and we're noticing the trend here for each additional side that we add and how that affects the number of triangles. So this guy would be 720. So notice now we have 5 triangles, so it's going to give us 900 degrees. This time we're going to get 1, 2, 3, 5. So that would be 6 triangles for this guy. would give us 1080 degrees. So what are we doing here? Well, we're taking our figures, splitting them into triangles. If we want to come up with a pattern that works in general for any convex polygon, we need to compare the number of triangles we get to the number of sides in the figure. And if we do that, we should be able to come up with some sort of rule that'll work for any polygon regardless of the number of sides. So let's say I look at this one. There were 4 sides, and I cut it into 2 triangles. Here I had 5 sides, and I had 3 triangles. When I got a 6-sided figure, or a hexagon, I ended with 4 triangles. Seven sides and 5 triangles. And hopefully you can figure out that as I go up, my number of triangles is always going to be 2 less than the number of sides. And since there's always going to be 180 degrees per triangle, my total number of degrees is always going to be 180 times the number of triangles. So the equation that I would use for any polygon is that I will take 180 degrees times the number of sides minus 2 that will give me the total number of degrees in any polygon as long as the sides point outwards like we are used to. One other quick thing to look at is the exterior angles. And so this is mostly going to work for regular polygons for this demonstration, but the idea here is going to be the same. Let's say we take this triangle and it's treated as equilateral. So these would each be 60 degrees because we know the total is 180, and we know that 180 divided by 3 would give us 60. We also know that the angles on the outside of the triangle, in other words, the angles formed by extending each of the sides, will form linear pairs with the angles on the interior of the triangle. So each of these guys would end up being 120 degrees. So if there's 3 sides, each exterior angle is 120. For each regular polygon with 4 sides, we know that would make a square, so these would all be 90 degrees. If it's 5 sides, right, we got 540 for the total degrees of the pentagon, which means each angle inside of the triangle would be 108 degrees, which means I would have 72 degrees on the outside. I'm going to end up with 120 degrees per angle for a hexagon, which means I'm left with 60 degrees on the outside, and we can keep going with the rest, but let's kind of look at what's happening here with the sums. So if I have 3 angles, each is 120 degrees, my total is 360. If I have 4 angles, each angle at 90 degrees, I have a total of 360 degrees. If I have 5 angles that each measure 72 degrees, I have a total of 360 degrees. If I have 6 angles that each measure 60 degrees, I have a total of 360 degrees. And so hopefully we are noticing the pattern that when we're dealing with external angles, the total is always 360 degrees. All right, that's all we have for today. I'll see you guys next time.